So, hello everyone again. This is lecture 10 part 2 of semiconductor electronics materials, devices and simple circuits. In this lecture we will move on with further discussions regarding the topic of transistor as a amplifier. In the previous discussion we understood basically the complete analogy, complete diagram of what was being explained as transistor as an amplifier. We understood we finally devised that AV is nothing but equal to minus beta AC into RB by RC, RC by RB, and then we let us understand more about it, and then finally we will try to mathematically calculate why we say that the final output voltage being obtained or final signal being obtained is 180 degree out of phase. So, let us start the discussion directly. So, I am Sameer Lavankar, let us begin our discussion. So, currently we are on the 9th topic, that is junction transistor. Let us move forward and understand what is being explained here in junction transistor as an amplifier. So, this is obtained in the previous discussion only, that is the voltage gain for this. Please remember that the complete analogy being explained here is only and only for common emitter transistor characteristics, transistors, fine. So, for a CE amplifier AV is obtained as, what is AV? AV is basically your small signal voltage gain. Okay. So, it is basically your small signal voltage gain. Okay. So, thus the linear portion of the active region of the transistor can be exploited for the use in amplifiers. So, that is how we basically use that active region for our explanation. Transistor as an amplifier is discussed in detail in the next section. So, let us understand now. So, to operate the transistor as an amplifier, it is necessary to fix its operating point somewhere in the middle of its active region. So, basically if you remember the graph correctly, if this is your V naught, if this is your Vi, so this is how the graph is. So, basically we are just trying to implement a range, a very area in which we can basically use an amplifier as a transistor as an amplifier. Okay. So, to operate a transistor as an amplifier, it is necessary to fix its operating point somewhere in the middle of its active region. If we fix the value of VBB corresponding to a point in the middle of the linear part of the transfer curve, and the DC base current IB, please remember why it is written as DC base current IB, because the complete value of IB being obtained is only and only due to input voltage. There is no addition and subtraction being done till now through the AC signal which is being explained or being added here in the diagram. So, therefore, it is being said that if we fix, so an assumption is being put here that if we fix the value of VBB corresponding to a point in the middle of the linear part of the transfer curve, then the DC base current IB would be constant. Quite evident, if the VBB is constant, RC is constant only, VBE will have no change, and hence IB will be constant, and corresponding collector current IC will also be constant, because the value or the change. So, every value of IB corresponds to a particular value of IC. So, if there is a constant IB being flowing through, then the constant IC will also being flown through. Hence, the DC voltage VCE, this was explained using Kirchhoff's rule. So, VCE is nothing but VCC minus ICRC will also be remain constant. Why? Because VCC is the output EMF, output EMF which will not change, it is constant only. As IB is constant, therefore, IC will also be constant, hence this is also constant, and RC will be constant only. So, hence we can directly say that a DC voltage would remain constant. Okay. Now, the operating values of VCE and IB determine the operating point of the amplifier. Okay. So, these are nothing but the steps, so that we can find exact point at which we should use the active region. So, if a small sinusoidal voltage with amplitude Vs. Now, this voltage basically due to that this signal. Okay. Now, we are trying to add this signal here. Okay. So, if a small sinusoidal voltage with the amplitude Vs is superimposed on the DC base bias. Okay. So, what we are trying to do? We are trying to add this voltage into this voltage like this. So, that it is being passed through this circuit, it is being passed through this circuit. Okay. So, if a small sinusoidal voltage with amplitude Vs is superposed on the DC base bias by connecting the source of that signal in series with the VBB supply, then the base current will have sinusoidal variation superimposed on the value of IB. So, what does it try to basically understand is, let us suppose that this is not being explained here till now. So, what is basically happening? Only current which is flowing here will be IB, correct. Now, what is happening, because of change in the value of voltage, there will be a change in the value of current also. So, there will be some plus value, let us say plus small I, value sometimes when the sinusoid is in positive direction, and there can be some value of minus I also sometimes. Okay. So, that is how they are trying to say that when an input AC signal is being added upon, there will be a change in the value of this IB dash, the current which is passing through the base, there will be a change due to sinusoidal variation or sinusoidal way of input. That is the first point. So, if a small sinusoidal voltage with amplitude Vs is superposed on the DC base bias, please remember this amplitude is AC signal and this DC base bias is DC signal. By connecting the source of that signal in series with the VBB supply, then the base current will have sinusoidal variation superimposed on the value of IB, fine. So, base current will be nothing but base current is that current which is passing through this base of the transistor. Fine. Next thing is, as a consequence, the collector current also will have sinusoidal variations, quite evident, because the value of IC is dependent on IB. If there is a change in the value of IB, there will be a change in the IC. If there is a sinusoidal variation in the value of IB, there will be a sinusoidal variation in the value of IC also. So, as a consequence, the collector current will also have a sinusoidal variation superimposed on the value of IC, producing in turn corresponding change in the value of V naught. So, as the value of IC will keep on changing, it will have an effect on VCE. What is VCE? VCE is the output voltage. Why? It will have a sinusoidal variation in the value of V naught also, because VCC and RC is constant. So, I hope I can make you understand how this amplifier concept is being worked upon. Okay. So, we can measure So, as a consequence, the collector current will also have sinusoidal variation superimposed on the value of IC, producing in turn corresponding change in the value of V naught. V naught is basically your output voltage. We can measure the AC variations across the input and the output terminals by blocking the DC voltages by large capacitors. So, that is another application of how large capacitors can be utilized if we need to understand only and only the usage, if we only and only input the AC signals. So, in the description of the amplifier given above, we have not considered any AC signal. In general, amplifiers are used to amplify alternating signals. So, in general, amplifiers are basically used because there is no usage of amplifying this concept. Majority of the signals which are basically used in household appliances or industries are basically alternating signal only. Fine. So, now let us move on to the mathematical concepts of understanding this. So, now let us superimpose an AC input signal Vi, which is to be amplified. So, this signal has to be amplified, okay, on the bias VBB. So, this is the bias VBB here, right, as shown in the figure. Okay. Next thing is the output is taken between the collector and the ground. As you can see that the output is taken between collector and the ground. The working of an amplifier can be easily understood if we first assume that Vi is 0. So, let us first assume, for the first case we should assume that Vi is 0, that is input signal has no effect, input AC signal has no effect or no value. So, first let us apply the value of Kirchhoff's rule to the output. So, this is already being done 2 to 3 times already. So, it is nothing but equal to your value of VCC is nothing but used by VCE plus ICRC, correct. And for next loop, this will be the value of VBB will be utilized by 2 things. One will be your VBE, that is base emitter junction, next will be IB into RB. Okay. So, these are the 2 equations first of all being explained here. So, first is VCC. So, this VCC, this, and next is this and this. Explaining again. So, in output what is happening? You are using this and this, and in input you are using this and this. Okay. Fine. That thing being said, so let then applying Kirchhoff's law to the output loop, we get, first of all, this is the equation number 1, let me put it here. Likewise, the input loop gives this. So, let me write this as equation number 2. Now, let us assume that Vi is not 0. Okay. So, if Vi is not 0, that is meaning it is having some value. If it is having some value, we can also understand that some sort of this is an EMF which is being applied here and applied here. The value of IB can be obtained as some delta IB here, right. So, only that concept is being utilized here. So, they are basically saying that the value of, so if we try to just add that value of Vi here, what will happen? So, it will be basically VBE plus Vi is nothing but equal to VBE plus what is Vi? Vi will be nothing but equal to IB RB plus delta IB into RB plus RI. Okay, try to understand this very carefully. I will try to explain you again. So, basically they are just saying that this Vi will have some resistance, some internal resistance. Let us assume that internal resistance to be Ri, right. Due to change or due to this value of Vi, there will be a small current being increased. So, small current it is having, let us assume that small current to be delta Ib. So, this delta Ib is due to that effect, correct, and this should be VBB, I guess, okay, and this IBRB is basically usage of this factor only, okay. So, it is nothing but VBB is equal to VBE plus IBRB, okay. So, first the first factor has this IBRB into consideration and this Vi has this factor into consideration, okay. Okay. So, that thing being said, now let us move on. So, the change in VBE, so the change in VBE can be related to the input resistance Ri and a change in IB, change in IB basically delta IB. So, they are just writing it like this. So, just some mathematical calculations are being done here and we finally obtained that what is Vi? Vi or the input AC signal is nothing but equal to small r. What is small r? Small r is basically input resistance into delta IB, into delta IB. Okay. Please remember delta IB and IB are different things. Okay. IB is basically the current which was being obtained due to this DC voltage being supplied from VBB, and delta IB is nothing but the voltage which is being obtained. Let us, we can also write this delta IB as some ID or IB dash also, right. So, that is basically obtained due to this alternating AC signal, fine. Next thing is, so the change in IB causes a change in IC, we already know normal properties of transistors. So, we now define a parameter AC. What is beta AC? Beta AC basically the amplification factor, which is similar to beta DC. So, therefore, now beta AC is nothing but equal to delta IC by delta IB, which is nothing but IC by IB, which is known as AC current gain AI. Okay. Please remember this is AC current gain AI. Usually beta AC is close to beta DC in the linear region of the output characteristics. This is just a normal fact given to you. The change in IC due to change in IB causes a change in VCE and the voltage drop across the resistor RL because VCC is fixed. So, they are just trying to say the same concept which we understood here also. So, basically they are saying that due to a change in delta IB, there is a change in delta IC. Due to change in delta IC, there is a change in this IC value, and due to change in this IC value, there is a change in this VCE. That is only being written here, because rest all things such as VCC, RC are constant. Okay. So, the change in IC due to a change in IB causes a change in the VCE and the voltage drop across the resistor RL because VCC is fixed. Okay. These changes can be given as, so how can we obtain these changes here? So, basically delta VCC is nothing, delta VCC is 0, we already know, because there can be no change in the value of VCC, is nothing but equal to VCE plus RL delta IC. So, therefore, we can write, so I am just writing it here so that we can understand this clearly. So, it is delta VCC is nothing but equal to delta VCE plus RL into delta IC. We know that delta VCC is nothing but equal to 0. So, therefore, we can directly write delta VCE, that is change in the common emitter current, sorry, common emitter voltage is nothing but equal to minus RL delta IC. Okay. Next thing is the change in the VCE is the output voltage V naught. So, therefore, what we can write? We can just write this simply has equal to V naught. Therefore, so this can be also obtained here from this as we know that the voltage difference across all these will be same. So, either we say this direction, I will say this direction, I will say this direction. Therefore, it is being said that this V naught is nothing but equal to this delta VCE. Okay. So, from previous equations we get V naught is equal to delta VCE, which is equal to, so this was being obtained previously here. So, therefore, we can directly write that V naught is nothing but equal to delta VCE minus beta AC into RL into delta IB. Okay. So, just inputting the values here, nothing new here. So, basically as you can obtain from this location also, that what is your value of IC? IC is nothing but equal to IC is nothing but equal to, or let me write it like this, small IC is nothing but equal to beta AC into IB. Okay. So, just using it in the place of IC we obtained V naught is nothing but equal to minus beta AC RL into delta IB. Now, let us again calculate the value of voltage gain. Okay. So, what is voltage gain? Voltage gain is nothing but equal to V naught by V I. What is V naught here? V naught is nothing but equal to delta V C E upon this will be nothing but equal to small r into delta I B. Okay. So, this was being obtained previous case here, as you can see V I is nothing but r into delta I B, and therefore, we can directly write it as equal to nothing but equal to minus beta AC into R L by small r. Please remember this very carefully. Here R L by small r is here, and you can see clearly that there is a negative sign being utilized here. This negative sign was the usage, or we can now mathematically also say that the output amplitude being obtained is in the negative direction as in the positive direction, or in another words, in physics terms we can say that it is 180 degree out of phase. So, if let us suppose that this is the input signal, then this will be your output signal. Okay. So, that was the basic concept which I was trying to explain to you. So, the negative sign represents the at output voltage opposite with phase with the input voltage. Okay. That thing being said, please remember this, that is A V is nothing but equal to minus beta A C into R L by small r. Fine. So, from the discussion of the transistor characteristics, you have seen that there is a current gain beta AC in the CE configuration. This is the current gain beta AC in the CE configuration. So, here we have also seen the voltage gain AV. As you can see here, you can also see a voltage gain also, you can see a current gain also. Therefore, the power gain AP can be expressed as the product of the current gain and the voltage gain. So, we already know in our current electricity concept what is power obtained. Power is nothing but equal to V into I, correct. So, they are just using the same concept for finding out the power gain or power being obtained due to change in this value of current also, due to change in this value of voltage also. So, this power is nothing but equal to V into I. So, therefore, in these terms we can write this power gain AP is nothing but equal to what was voltage gain was basically AV, and what was your this current gain is nothing but beta AC or the amplification factor, correct. So, this is how you can understand this concept, and therefore, this is the new formula. So, this is normal, this is nothing new, no new concept being utilized here. We are just finding out the power gain, we are just finding out the voltage gain, we are just finding out the current gain, and we are writing that AP is nothing but equal to AV into beta AC. Okay. So, since beta AC and AV are greater than 1, as this is also greater than 1, as this is also greater than 1. So, we can get AC power gain also, which is greater than 1. Okay. However, it should be realized that transistor is not a power generating device. The energy for the higher AC power at the output is supplied by the battery. Okay. So, this is just a normal fact which we need to understand, that the transistor cannot be used, or it is not a power generating device. It cannot give you more power. So, even if you do these all things, you can see that there is an increase in the power, that power cannot be utilized. The power which can only be utilized will be that which will be supplied by the battery. The energy for the higher AC power at the output is supplied by the battery. So, the amount of power which that new output amplified signal requires will be input by the, or will be using only the battery voltage, battery EMF will be used there. This power gain value or this power gain use requirement cannot be used for the subsequent part for working of that increased amplified voltage or increased amplified current. Fine. So, that thing being said, I think this is the end of your transistors and amplifier. In the next class, we will just do two simple examples regarding this concept. One was, I think one question is regarding the switch, and second question is regarding the amplifier, and then we will move on to the final concept of this transistor, which is the application of transistor as an oscillator. So, let me stop it here only. We will continue in the next part of this lecture. So, thank you so much.